So, welcome back to third session of coordination chemistry. I hope everything is clear in the last session where I discussed about awareness theory, valency bond theory, Sidgwick's theory. Now, in this session, I would like to discuss about applications of valency bond theory. That is geometries of 4 coordinate complex and geometries of 6 coordinate complex. The first, let's look at the geometries of 4 coordinated complex. Okay, so geometries of 4 coordinate complex. Let's take an example. NiCl4 2 minus. NiCl4 2 minus. So first, what is the IUPAC nomenclature for this complex? This is an anionic complex because we are having negative charge over the complex. Okay, now tetrachloro. First, starting with the ligands. Tetrachloronickelate because we are having negative charge over the complex. So 8 ending with metal atom name ending with 8. So tetrachloronickelate. Oxidation state here. What is the oxidation state of nickel here? You just calculate. You don't know oxidation state of nickel here. Let us assume X plus 4. We are having 4 ligands. 4 into each chlorine. So over the chlorine we are having negative charge. That means minus 1, which is equal to overall charge over the coordination sphere, that is minus 2. So X equal to 4 minus 2, X equal to plus 2. So the oxidation state of nickel in this complex is plus 2 oxidation state. Okay, right. So tetrachloronickelate to ion because it is having charge over the complex. So we just mention ion. So tetrachloronickelate to ion. Okay, right. Now for this complex, now we have to determine hybridization, magnetic properties, and the structure. Okay, right. First, nickel here I already calculated oxidation state of nickel here plus 2. Now first we have to write nickel atomic number, that is nickel is 28. Nickel 28. And the electron configuration is argon 3d8 4s2, argon 3d8 4s2, and nickel oxidation state here in ground state actually it is nickel in its oxidation state, that is 2, nickel plus 2. So nickel plus 2, that means losing 2 electrons, So those 2 electrons losing from here 4s is outermost shell. So 2 electrons are removing from outermost shell first. So electrons are removing from 4s orbital. So the electron configuration will become here argon. So 3d8 4s 0. So electrons entered into the 4 shell. So 4 shell we are having a s orbital, p orbital, d orbital, and f orbital. So empty 4p 0 and 4d 0. Okay. So 3d8. So 3d8 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons. Okay, and 4s 0. So and 4p 0 and 4d 0. I am having 5 d orbitals here. So we are having 3 p orbitals, px, py, pz. And here how many d orbitals? 5. dxy, dyz, dzx, dx square y square, and dz square. Okay. Now in this complex NiCl4 2 minus NiCl4. Now 4 chlorines. Each chlorine is 1 lone pair of electrons. So how many lone pair of electrons donated by chlorine here? 4 into 2. Total 8 electrons and 4 lone pairs donated by these 4 chlorine atoms. So nickel needs 4 vacant orbitals. Okay. Now one more thing is here. So chlorine is weak field ligand. In the previous lecture I am telling you. So what I told you. So weak ligands are classified into strong ligands and weak ligands. So examples of strong ligands are carbonyl, CO, cyanide, okay, NO2 minus. All these are examples of strong ligands. And chlorine, halogen atoms, water molecules, Cl minus, F minus, Br minus, OH minus, H2O. So all these are NH3. All these are weak ligands. So weak ligands they follow according to Hund's rule. Okay, that means here the electrons are filled as it is Hund's rule like this. So 1, 2, 3, 4, 5, 6, 7, 8. Now 4s 0 and 4p 0. Now each chlorine unit 1 lone pair of electron. Here 1 chlorine unit 1 lone pair of electron into this 4s orbital, and next 4p orbital. So you are having, so 1 second chlorine donates 1 lone pair of electrons to its into its empty orbital of 4p, and third chlorine and fourth chlorine. So now how many empty orbitals are available here for accepting electrons from ligand? Here 1 s orbital, 3 p orbitals. So 1 s orbital, these 3 p orbitals are mixed together, which gives sp3 hybrid orbitals. So we are having 4 sp3 hybrid orbitals. So these 4 sp3 hybrid orbitals are overlapping with chlorine orbitals, ligand orbitals. Okay, right. So hybridization is sp3. In the previous video, I am giving one table. At the end of that lesson, I am giving one table. So where the coordination number is 4, the hybridization is sp3. If the coordination number is 4, maybe sp3 or dsp2. If it is sp3, the shape is tetrahedral. If it is dsp2, the shape is square planar. Here sp3. Hybridization is sp3. So because of hybridization is sp3, the shape of this molecule, this complex is tetrahedron. That means nickel, CO, 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 CO. This is the structure of tetrahedron. Okay. So, and next, so first thing is hybridization. Hybridization of this complex is sp3, and the second thing is structure. Structure is sp3. So hybridization is sp3. So shape is shape. Hybridization is sp3. Shape is tetrahedral. Tetrahedral. Shape is tetrahedral. And the magnetic properties. So magnetic property. So magnetic property is, so magnetic property. So how can you know magnetic property, whether it is diamagnetic or paramagnetic? So here if any at least one unpaired of electron after formation of complex, after approaching of chloride ions forming this type of complex, if you are having any at least one unpaired of electron, that complex is having paramagnetic nature. Okay, at least one unpaired of electron. The complex should contain at least one unpaired of electron. So that is right. If you are not having any unpaired of electron, so that complex is diamagnetic in nature. Okay. So for example, the C complex. So here two unpaired of electrons. So this complex is paramagnetic. So paramagnetic with respect to two unpaired of electrons. Now here you can calculate magnetic momentum also. So magnetic momentum. So mu is equal to square root of n into n plus 2 Bm, Bohr magneton. Okay. So n into n plus 1, where n is number of unpaired of electrons. Here having two unpaired of electrons. So square root of 2 into 2 plus 2. So that is square root of 2 into 4 root 8. So root 8 around 2.9. So 2 point around something 85 around Bohr magneton. Okay, right. So I repeat it again. So NaCl4 2 minus. So if you want to determine hybridization and the shape and magnetic properties, first you have to know electronic configuration of the center metal atom. So here center metal element is nickel. Electronic configuration is 3d8 4s2. And here nickel present in +2 oxidation state, so losing 2 electrons from its outermost shell, and then here we are having 4 chloride atoms. So each chlorine donates 1 lone pair of electrons. So nickel needs 4 vacant orbitals. So what are those 4 vacant orbitals? 1 s orbital, 3 p orbitals. So now donating 4 chlorine atoms, donating 4 lone pair of electrons to the center metal atom and forming this type of bond. Okay. Right. So 1 s orbital, 3 p orbitals mixed together, which gives sp3 hybridization. These sp3 hybrid orbitals of metal overlapping with the orbitals of carbonyl, forming this coordinate covalent bond. Okay. Next, shape of the molecule. Here hybridization is sp3, so shape is tetrahedral. And coming to magnetic properties. So if you are having any at least one unpaired of electron after formation of complex, if you are having any at least one unpaired of electron, that complex would be paramagnetic. Here having two unpaired of electrons. So this complex is paramagnetic. Okay. Let's see another example. CN4 2 minus, NiCN4 2 minus. So here first we have to find out oxidation state of center metal atom. So what is the oxidation state of center metal atom? Here center metal atom is nickel. So what is the oxidation state of nickel in its complex? So here you have to calculate. So let us say x plus 4 into over the cyanide we are having negative charge, minus 1 charge. So 4 into minus 1, which is equal to the charge over the complex, that is minus 2. So x equal to plus 2. Here also we are having plus 2 oxidation state, nickel present in its plus 2 oxidation state. Okay. Next, now nickel electron configuration is 3d8 4s2, 3d8 4s2, nickel plus 2 oxidation state, nickel plus 2 oxidation state. So here electrons, so 3d8 4s 0 and 4p 0 and 4d 0, right. So here 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now we are having 4 cyanide ligands. So 4 cyanide ligands, each cyanide ligand donating 1 lone pair of electrons. So NiCN4 2 minus. So which is, so 1, 2, 3, 4, 5, 6, 7, 8. So why here? Cyanide is strong ligands. Cyanide is strong ligand. So strong ligand. So why it is strong ligand? Why chlorine is the weak ligand? I will explain in detail in the next lesson in Kirsta field theory. So where you can get clarity about strong ligands and weak ligands. All those things I will discuss in that theory, that is Kirsta field theory. Okay. So now you just understand cyanide is strong ligand. So strong ligand means which have tendency to pair up electrons. So electrons are paired against to Hund rule, that is 1, 2, 3, 4, 5, 6, 7, 8 electrons are paired up, tendency to that means against to Hund rule electrons are paired up. So that means now, so what are the 4 vacant orbitals? Here having 4 cyanide ligands now. So each cyanide ligand donating 1 lone pair of electron. Total you need nickel needs 4 vacant orbitals. So what are those 4 vacant orbitals? First thing, so let us count from this orbital, that is d x square y square. So this is dx square y square, and 1 d orbital, 1 s orbital, and 2 p orbital. So dsp2 hybridization, dsp2 hybridization. So dsp2 hybridization is dsp2 hybridization, and shape is square planar. So because of hybridization is dsp2, the shape is square planar geometry. The next, magnetic property. So magnetic property. So magnetic property, here you don't having any unpaired of electrons here, all are paired up. So you don't have any, at least you don't have even 1 unpaired of electrons you not get here. So it is diamagnetic because of no unpaired of electrons. So it is diamagnetic, right. So this is NiCN4 2 minus. Next, so square planar shape here, Ni cyanide, 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 Cn, 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 Cn. Okay. So this is shape of NiCN4 2 minus. Next, so NiCO4 2 minus, NiCO4 2 minus, NiCO4. So this is neutral complex. So carbonyl is neutral. Over the complex we are having 0 oxidation state. So nickel oxidation state here 0. Nickel oxidation state here 0. That means nickel, second 4 argon 4s2, 3d8 4s2, 3d8 4s2, and oxidation state of nickel here 0. So no loss of electrons here, 3d8 and 4s2 and 4p 0, and we are having 4d 0 vacant orbitals, right. And next, in this complex, the nature of ligand. Okay, let's see the nature of ligands. Carbonyl is strong ligand. So carbonyl is strong ligand. So, strong ligand, so it is pair up electrons, tendency to pair up electrons. So, NiCO4 the complex while forming the complex, because of this CO is strong ligand, the electrons present in d orbitals are paired up. Okay, because of the strong ligand, because of the strong effect of this carbonyl ligand, the electrons present in d orbitals and s orbitals, all these are paired up. That means so 3d, so these two electrons are paired up in this d orbital. So 3d 10, 4s 0 and 4p 0. That means so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these two electrons are jumps into the electrons present in s orbital jumps into the 3d orbital. So here having 3d10 electronic configuration, 4s0 and 4p0. Now how many carbonyl ligands are you having? So how many? 4 carbonyl ligands. So each carbonyl ligand donating one lone pair of electron, right? Now here nickel requires 4 vacant orbitals. So what are those 4 vacant orbitals? Let's count. So from s orbital 1, 2, 3, 4, one carbonyl donates its lone pair of electrons into the s orbital. So second carbonyl donates its lone pair of electrons into the p orbital, and then third and then fourth. So one s orbital and 3 p orbitals. Hybridation is sp3 hybridation. Hybridation is sp3. So shape is here sp3 hybridation. The shape, the geometry of the molecule is tetrahedral. So tetrahedral. So tetrahedron means tetra means 4, hedron faces. Hedron means 4 faces. So you are having 4 faces in the structure. Okay. Magnetic properties. So magnetic properties. So here you are having any unpaired of electrons? No. So all are paired up. Okay. So no unpaired of electrons. So this complex is diamagnetic in nature. So magnetic momentum is 0. Square root of n into n plus 2 Bm, Bohr, where n is unpaired of electrons. Here I don't having any unpaired of electrons. So n in the place of n you have 0. Replace 0. So square root of 0 into 0 plus 2, that comes out to be 0. The magnetic moment is 0. So this complex is diamagnetic in nature. Diamagnetic property. Okay. So this is all about 4 coordinated complexes. Right. In this way, you just try COCl4 2 minus. Okay. So you just try what is the hybridation of this complex, and what is the shape of this complex, and what is the magnetic nature of this complex, is it dia or para. Okay. If you are having an unpaired of electrons after formation of complex, so that is paramatic. If you have not having any unpaired of electrons, so that is diamagnetic in nature. Okay. You just try this complex. Okay. Next, geometry of 6 coordinated complexes. Geometry of 6 coordinated complexes. Right. 6 coordinate complex means octahedral complexes. 4 coordinate complexes either form tetrahedral or square planar. Okay. If the hybridation is sp3, that is tetrahedral. If the hybridation is dsp2 or sp2d, so that is square planar. Okay. So this is the defect in Werner's theory. So Werner's theory and Zilberg's theory doesn't explain why some 4 coordinate complexes are forming tetrahedral, others are forming square planar. So that defect can be explained by this Valency bond theory. Okay, based upon hybridation. Right. Next, in 6 coordinate complexes, here having outer I am telling you 2 types of complexes. So what are those outer optic complexes, inner optic complexes? What is outer optic complexes? In the hybridation, outer d orbitals are involved, so those complexes are outer optic complexes. In the hybridation, inner d orbitals are involved, so those complexes are inner optic complexes. First, let's see inner optic complexes. Inner orbital complexes, inner orbital complexes, right. So inner orbital complexes, example CONH3 6 times 3 plus. Let's take an example, CONH3 6 times 3 plus. Here coordination number is 6. Coordination number is 6. 6 ammonia molecules donates electron pairs. to this cobalt, which is present in +3 oxidation state. Cobalt oxidation state here. So ammonia having no charge, so not having any charge. So this is neutral molecule, neutral ligand, because we don't having any charge over this molecule. So this is neutral molecule. So over the complex we are having +3. So this is 0, and over the complex we are having +3. So this charge belongs to this cobalt. So that is oxidation state of cobalt here +3. Oxidation state of cobalt is +3. First we write down what is the electronic configuration of cobalt. So argon. So cobalt is 27. So 27. So last year 7. So 4s2 3d7 or 3d7 4s2. So 3d7 4s2 and 4p0 and 4d0. Okay. Now so 3d7 4s2, right. So cobalt here oxidation state is +3. Cobalt oxidation state here +3. X plus 6 into 0 equal to +3. X comes out to be +3. Oxidation state of cobalt here +3. So cobalt oxidation state +3. So that means cobalt losing 3 electrons. +3 means losing 3 electrons. Okay. So those 3 electrons here, first 2 electrons are lost, removing from 4s orbitals, because 4s is outermost shell now. So first 2 electrons are removed from 4s, one more electron is removed from 3d7. So the electron configuration becomes 3d6 4s0 and 4p0 and 4d0. Okay. So 3d6 4s0 4p6. So 1 2 3 4 5 6. Okay. And 4s0 and 4p0 and 4d0, right. Now next, what is the nature of this ammonia? So ammonia acts as a strong ligand when metal atom is present in higher oxidation state. Ammonia acts as a strong ligand when the central metal atom is present in higher oxidation state. Here ammonia is present in a higher oxidation state, that is +3. If the cobalt is +2 oxidation state, that is lower oxidation state. So this ammonia, in that time ammonia acts as a weak field ligand, that means weak ligand. Here cobalt are present in +3 oxidation state, that means higher oxidation state. So ammonia acts as a strong ligand. So that is important thing, that important point you have to keep in mind. Okay. CONH3 6 times 3 plus. So because of this strong effect of this ammonia, because of strong ligand, so the electrons present in d orbitals are paired up. So this becomes electron configuration becomes, so 1 2 3 4 5 6. So because of strong ligand of this amine, so strong field ligand, ammonia is a strong field ligand, so electrons are paired up. So paired up, and 4s0 and 4p0. Now how many empty orbitals are available in cobalt required for bonding with the ammonia? Here having 6 ammonia molecules. So 6 ammonia molecules. So cobalt needs 6 vacant orbitals. So what are those vacant orbitals? Let's count down from here. 1. So this is dx square y square, and this is dz square. dxy dyz dxy dyz dzx dx square y square dz square. So dx square y square and dz square, and 4s and 4p. So one ammonia donating its lone pair of electrons into its dx square y square orbitals. 1 2. Second ammonia donating its lone pair of electrons to the dz square orbital, and third, fourth, fifth, and sixth. Okay. So 2 d orbitals, and so 2 d orbitals, 1 s orbital, and 3 p orbitals. So overall d2 sp3 hybridation. So hybridation is d2 sp3 hybridation. Here we are having a 4d. So this outer d orbitals. Here we are having 3d inner d orbitals. So in the hybridation, so what d orbitals? So those d orbitals are involved here. So inner d orbitals are involved in this hybridation. So 3 d orbitals are involved in this hybridation. So this complex is the inner orbital complex. Okay, because of in the hybridation 3 d orbitals, that means n minus 1 d orbitals are involved. If n d orbitals, that means 4 d orbitals are involved, that is sp3 d2. So that those complexes are called outer orbital complexes. Now this complex is inner orbital complex because of inner d orbitals involved. Okay, so most probably strong field ligands forming inner orbital complexes. In most cases, strong field ligands are forming inner orbital complexes. Right? Hybridation is d2 sp3, and the shape is octahedral. Okay, hybridization due to sp3, shape is octahedral, and magnetic property. So magnetic property is, so here, so you are having any unpaired of electrons? No. Okay, all are paired up. So this paired electrons, these are paired electrons, these are also paired electrons. So you don't having any unpaired electrons. So this complex is diamagnetic in nature. Diamagnetic in nature because of no unpaired of electrons, right? So first hybridization is due to sp3, shape is octahedral, and magnetic property is diamagnetic. Okay, I hope everything is clear. Okay, next let's take another example for better understanding. Or you may try so FeCN6 3 minus, FeCN6 3 minus. So FeCN6 3 minus, what is the hybridization of this complex, and magnetic property, and obviously shape is octahedral because the coordination number is 6, the shape is octahedral. So it is inner orbital complex or outer orbital complex, that you have to predict from hybridization. Okay, right. Next, outer orbital complex. So this complex you have to try. Okay, so you need to pick your pen and paper and write down and practice. Next, outer orbital complexes. So outer orbital complexes. So outer orbital means in the hybridization outer d orbitals are involved. So let us take an example. COF6 3 minus. COF6 3 minus. Here fluorine is weak ligand. All halogens are weak ligands. Fluorine is weak ligand. Oxygen state of cobalt here. So x plus 6 into fluorine is minus 1 and equal to overall charge minus 3. X equal to 6 minus 3. It is comes out to be plus 3. Oxygen state of cobalt here plus 3 oxygen state. Okay. Now cobalt is 27. So 4s2 argon. 3d7 4s2. So cobalt 3. So losing 3 electrons. So first 2 electrons are losing from its valence shell, that is 4s, and one more electron lose from its d orbital, that is 3d6. So the electron configuration becomes 3d6, 4s0, 4p0, and 4d0. Okay. Now forming complex, 6 fluorine atoms are approaching along with their electron density towards ligand. So towards metal atom. So how many vacant orbitals are required for cobalt for accepting electrons from fluorine? So 6 fluorine atoms, each fluorine donates one lone pair of electrons. So cobalt requires 6 vacant orbitals. So 3d6, 4s0 and 4p0 and 4d0. So 3d6. Here the point is nature of fluorine. So fluorine here weak ligand. So it follows according to Hund's rule. First you have to fill degenerate orbitals and then paired up. So 5 and then 6th, which is paired with this unpaired of electron. Okay. Next 4s0 and 4p0 and 4d0. Right. So now 6 fluorine atoms donating 6 lone pair of electrons to the cobalt. Now let's count them from here. So here vacant orbital 1 fluorine donates its lone pair of electrons into the s orbital of cobalt, and second fluorine donates its lone pair of electrons into the p orbital, and third fluorine and fourth fluorine, fifth and sixth. Okay. 6 fluorines donating its 6 lone pair of electrons into this metal vacant orbitals. So 1 s orbital, 3 p orbitals and 2 d orbitals. So sp3 d2. sp3d2 hybridization. So sp3d2 hybridization. So he in this hybridization, so what d orbitals are involved? Which d orbitals are involved here? So either in inner d orbitals or outer d orbitals. Yes, outer d orbitals. So outer d orbitals involved in the hybridization. So this is outer orbital complex. Okay. So 3d and 4d. 4d is outer and 3d is inner. In the hybridization, these 2 d orbitals are involved. The outer d orbitals are involved. So hybridization is sp3d2. Hybridization is sp3d2. outer d orbitals are involved. So, this is outer orbital complex, and the geometry. So, geometry is octahedral. Geometry is octahedral, and the shape, magnetic property. So, magnetic property is, so here you are having 4 unpaired of electrons, 1, 2, 3, 4. So, 4 unpaired of electrons. So, this is paramagnetic nature corresponding to 4 unpaired of electrons. Okay. Similarly, as many complexes as you can do. Okay. Let's take, you just try FeNH3 6 times 2 plus. So, ammonia is here a weak ligand because Fe present in +2 oxygen state, lower oxygen state. Okay. And NiNH3 6 times 2 plus. So, here coordination number is 6, coordination number 6. So, absolutely both are outer orbital complexes, both are forming sp3d2 hybridation. You just find out. Okay. Similarly, last question also, FeCN6 4 minus, you can predict both 3 minus. Okay, you can predict hybridation, shape and magnetic properties. So, both are same center metal atoms, same ligands, same coordination number, but the difference is oxygen state. Here oxygen state is +2, here oxygen state is +3. Okay, ferrous, ferric. Now, so what is the difference here? Here it is FeCN6. So, Fe +2 oxygen state, here Fe +3 oxidation state. So, 4s 3d6. So, Fe27 Fe26 4s2 3d6, 4s2 3d6. So, 3d6 4s2. So, 4s2 losing 2 electrons, 4s 0 and 4p 0. So, cyanide is strong ligand, in both the cases cyanide is strong ligand. So, here also, here it is losing 3 electrons, +3 means losing 3 electrons, 2 electrons from s orbital, 1 more electron from d orbital, that means 3d5, 4s0 and 4p0. Okay. Here hybridation is 3d6, 1, 2, 3, 4, 5, 6. Okay. 2 more vacant orbitals here, here and here. So, D2 sp3 hybridation, inner orbital complexes, D2 sp3 hybridation. Now, coming to this complex 3d5, again S2 Hund's rule, 1, 2, 3, 4, 5. Here it is 6, 3d6, 3d5 and 4s0 and 4p0. So, sp3 d2, here also sp3 d2, sp3 d2, here also sp3, both hybridation is same, but magnetic shape is same. Octahedral complex, both are octahedral complexes, both are involved in hybridation sp3 d2 hybridation. Okay. Now, the difference is here having one unpaired of electron, here having one unpaired of electron, that means this complex is having around 1.73 magnetic momentum, Bohr momentum. Okay. Now, here it is 0 magnetic momentum, so 0 magnetic momentum because we are not having any unpaired of electrons, Okay. So, this is diamagnetic nature, this complex is dia and this complex is paramagnetic. So, the difference is magnetic nature. So, same hybridation sp3d2 inner orbital complexes, okay, same geometry octahedron, but the difference is this complex is dia, this complex is para. Okay, right. So, you just try your own examples, you can frame different types of complexes and just try, just calculate oxygen state of center metal atom. Let's see what is the nature. So, nature of, so strong field ligands, strong field are CO, Cn minus, NO2 minus, orthophenanthrene, bipyridine, okay, and weak ligands. So, weak ligands are halogens, fluorine, chlorine, so bromine, H2O, OH minus, and in some cases ammonia. So, ammonia acts as a strong ligand when the center metal atom having higher oxygen state, and acts as weak ligand when the center metal atom has a lower oxidation state. Okay. So, this thing you have to keep in mind. If it is a strong ligand, the electrons are paired up, has tendency to pair up electrons. The electrons present in d orbital are paired up. Okay, and if it is weak ligand, if you can fill up as it is. Okay, you can fill up by following Hund's rule. Okay, right. Now defects of Werner's theory. Defects of valency bond theory. So what are the defects of valency bond theory, VBT? The first defect is, so this theory unable to explain the color and spectra of metal complexes. This theory unable to explain color. What are the complex having color? So and spectra of that metal complexes. Okay. Next, this theory unable to explain relative stabilities and strength of ligands. Relative stability and strength of different ligands or various ligands. Okay, this is second defect. So first defect is unable to explain color of the complexes and spectra of the complexes, cannot explained by this theory, valency bond theory. And second thing is relative stability and strength. So which one is strong ligand, which one is weak ligand, that means the stability and strength of ligands. So not explain satisfactorily, not explaining stability and strength of the various types of ligands. And it is not explained temperature dependent paramagnetism. Temperature dependent paramagnetism. Okay, how the magnetic behavior varies with the temperature. Okay, so that thing is not explained by this theory. And next, splitting of metal d orbitals. So this thing can be explained by Kirsta field theory. Next theory, I will explain you that theory. So splitting of metal d orbitals cannot be explained by this theory, valency bond theory. So these are the few defects regarding valency bond theory. Okay, and the next theory, sorry for the disturbance. Okay, the next theory, Kirsta field theory. So this is very most important theory, Kirsta field theory, CFT, most important theory in coordination chemistry. So which explains, so valency bond theory cannot satisfying all the properties of complexes. Now after that, valency bond theory, so Kirsta field theory explained by, developed by Bill and Van Vleck. So in order to explain color, so which is not explained by valency bond theory, color of different complexes. Okay, and spectra of metal complexes and magnetic spectra and magnetic behavior. Magnetic behavior of different complexes, right? Right. So the first assumptions of Kirsta field theory. So Bill and Van Vleck made a few assumptions. Let's see one by one. The first assumption was the bond between metal and ligand. The coordination sphere having metal and ligand. So the bond between metal and ligand is assumed to be ionic. The bond between, according to Kirsta field theory, the bond between metal and ligand is assumed to be ionic. That is first assumption. And the second assumption, ligands are considered as point charges. Ligands are considered as point charges or point dipoles. Ligands are considered as point charges. If you are having any charge over the ligand, that would be considered as point charge. If you are not having any charge, that is neutral ligands, that would be considered as point dipoles. Okay. Next, so there is the electrostatic attractions. So because of the bond is ionic, there is electrostatic attractions between the metal and ligand. Electrostatic attractions between metal and ligand. So these electrostatic attractions are maybe ion-ion attractions, or ion dipole attractions. So ion attraction in the case of so both are ions, that is metal having positive charge. If your ligands is negative charge, if your ligands are having negative charge over the molecule or the atom, if you are having negative charge, that is ion, considered as ion, and metal having positive charge and ligand having negative charge. So both are ion. So that the interaction between those two ions are having electrostatic attractions. Those attractions are ion attractions. Okay. And next, ion dipole attractions. So metal and ligand both are charged. This is positive and this is ligand. So those then attraction between these two are ion attractions. Ion attractions. And next thing is ion dipole attractions. The metal having positive charge and the ligand is neutral. Okay, ligand is neutral. So then attraction is ion and this neutral ligand considered as dipole. Okay, so ion dipole attractions between charged, positive charge in metal atom and neutral ligand. So this is third assumption, right? And then fourth assumption. So this theory mainly concentrated on metal d orbitals. Metal d orbitals. So metal d orbitals. You know how many metal d orbitals? How many metal d orbitals? So how many d orbitals? dxy, dyz, dzx, dx square, y square and dz square. Total 5. If your answer is 5, yes, you are correct. But in fact, there are 6 d orbitals: dxy, dyz, dzx, dx square y square, and then dy square z square, and then dz square x square. Now the last two, dy square z square and dz square x square, both are combined linearly. Here get dz square. Both are combined linearly, forming dz square orbitals. So this is dy square z square and dz square x square. So these are combined linearly. You are getting dz square orbital and d x square y square, dxy, dyz and dzx. So total we are considering 1, 2, 3, 4 and 5. So in fact generally there are 6 d orbitals, but these two are combined linearly, can get dz square orbital, right? So 1, 2, 3, 4, 5. So you are having 5 d orbitals. Okay. So in the metal you are having 5 d orbitals. These 5 d orbitals, when ligands are approaching with their electron density, in these metal d orbitals also having electrons now. These d orbitals, the metal d orbitals which contains electrons, and the ligands also approaching electrons with their electrons approaching towards metal atom. So then there is a electron repulsions between the metal d electrons and ligand electrons. Okay, metal having electrons and ligands also donating electrons into this vacant orbitals. Now there is a electron repulsion. Because of this electron repulsions, there is a slight increasing of d orbitals. Metal d orbitals, energy of metal d orbitals increases. Okay, so before ligands approach, before complex formation, that means metal in free state, all the 5 d orbitals, those are dxy, dyz, dzx, dx square, y square and dz square. So all these 5 d orbitals are degenerate. Degenerate means same energy. All these 5 d orbitals are same energy. All these 5 d orbitals are same energy when metal in free state. When ligands are approaching with their electron density, so there is a electron repulsions. These 5 d orbitals, in these 5 d orbitals you are having metal d electrons. So these electrons and ligands also approaching with their electron density. There is a electron repulsion. So these 5 d orbitals energy rises somewhat. So energy rises. Okay. So that is fourth postulate, fourth assumption, and the fifth assumption was so because of ligand influence, because of ligands are approaching either along the axis or in between the axis. Under the influence of ligands, the metal 5 d orbitals are split into two sets. So dxy, dyz. So dxy, if you see the structure of dxy, so plus, minus. So loops are in between the axis. So this is x axis and this is y axis, x axis and y axis. dyz, yz. dzx. Okay, dxy, dyz, dzx. So these three orbitals are having electron density in between the axis. Loops are in between the axis. That means electron density are in between the axis. And next remaining two, dx square y square and dz square. So dx square y square. X, y. So loops are along the axis. Loops are along the axis. That means electron density along the axis. Okay, now this is dz square. Dz square which is linear combination of dy square z square and dz square x square. Okay, right. So or this dz square also loops are along the axis, along the z axis, and also some electron density along y axis and x axis also, because here the electron density here this is dz square is linear combination of dy square z square and dz square x square. Okay, right. So these are the all these 5 d orbitals, all these 5 d orbitals. So 3 d orbitals are the loops are present along in between the axis. Remaining 2 d orbitals, this is dx square y square and dz square. So both these orbitals are along the axis. Now these 3 orbitals are called as T2g orbitals. These 2d orbitals are called as Eg orbitals. So what is T2g? What is T2g? Triple E, 1, 2, 3, triple E degenerate. Both all these 3 orbitals having same energy because they are having same structures na. So 1, 2, 3 loops are in between the axis na. So all these 3 orbitals having same energy. Same energy means degenerate. So triple E degenerate Gerard orbitals or Gerard. Okay, so triple E degenerate Gerard orbitals. Gerard means So Gerard means if I having center of inversion plus and plus and minus minus. So these orbitals having center of inversion. If I having any center of inversion, we should use G Gerard. Okay, right. In this Eg. So Eg stands for 1, 2. So doubly degenerate. Here also having center of inversion, right? Center of symmetry, right? So 1, 2. So 2 d orbitals. So doubly degenerate Gerard orbitals. Doubly degenerate Gerard orbitals. Now, right, if the ligands. So what I am telling you, what is the fifth postulate? Under the influence of ligands. If the ligands are donating with their electron density, approaching with their electron density along the axis, Now along the axis, that means these two. So there is a repulsion between Eg orbitals and ligand orbitals. So more repulsions between Eg orbitals and the ligand orbitals. If electrons are donating along the axis, if electrons are donating, if the ligands are donating with electrons in between the axis, in that case T2g orbitals having more repulsions, more energy. Okay, that means so what I am telling you is, so what I am saying, so all these 5d orbitals split into 2 sets. All these 5d orbitals, initially you are having 5 degenerate orbitals. Under the influence of ligands, these 5d orbitals split into 2 sets. Okay, so T2g, Eg. So this is Eg. So which one is higher energy? That depends upon ligands approach. If the ligands are approaching along the axis, then Eg orbitals experience more repulsions. In that case, Eg having higher energy, more repulsions, more energy. In case ligands are approaching along the axis, in between the axis, T2g orbitals experience more repulsions. In that case, T2g orbitals are more repulsions. So that is depends upon shape of the molecules. Okay, I will explain in detail in the next class. So structures are different geometries of complexes, how many, so are the splitting of d orbitals in different various geometries. Okay, I will explain in detail in the next video. Right. Okay, so what is fifth postulate? Under the influence of ligands, the 5 degenerate orbitals are split into 2 sets. The difference between these two, the splitting is called Kirsta field splitting. The splitting is called Kirsta field splitting. The energy difference is called Kirsta field stabilization energy delta, which is indicated by delta. In case it is octahedral complex, the suffix, that means here the suffix is superscript is subscript is O. In case tetrahedral, T. Okay, right. So that is fifth postulate. Next, sixth postulate. So what is the sixth postulate? Right. So sixth postulate, that is magnetic property. Magnetic property. So magnetic property of a complex compound depends upon extent of this splitting of d orbitals. If the extent of splitting of d orbitals increases, extent of d orbital splitting increases, the electrons, instead of electrons going into the fourth orbital, that is easy orbitals, the electrons are paired in the ground state, paired in the T2G level. Okay. So if this magnetic property which is depends upon the extent of d orbitals, if the extent of d orbitals is more, the electrons are, instead of going into the higher energy, so they are paired up in the lower energy. That means unpaired of electrons decreases, hence magnetic character decreases. That means if the splitting is more, magnetic character is less, since less unpaired of electrons, right. So that is magnetic property. Next, color. So color of complex compounds can be explained by the electronic transitions. In the ground state here having electrons na, so these electrons are moving into the excited into the this higher energy Eg when absorbing light, the visible light. So again it comes back into the ground state by emitting somewhat light which is corresponding to wavelength. So this can spectra and color of complex compounds, all these things are explained in the next second lesson, unit 2, spectra and color of complexes. In that chapter I will explain color of complex compounds. Okay, right. So these are the postulates, few postulates of Kirsta field theory. For quick revision, let's see. So first, Kirsta field theory. So Kirsta field theory, which is developed by Beath and Van Vleck in order to explain color, spectra, and magnetic properties of crystalline solids, crystalline complexes, right? So they made few assumptions. The first assumption is metal and ligand. The bond between metal and ligand is purely ionic, assumed to be purely ionic. That's first point. And the second postulate was there is a electrostatic. The ligands are considered as point charges. Ligands are considered as point charges or point dipoles. So ligands are considered, if ligands have over the atom molecule which have negative charge, any charge, so that is point charges. If you are not having any charge, so that would be considered as point dipoles, right? Ligands are considered as point charges or point dipoles. And the third postulate. So what is the third postulate? So here the bond is ionic bond. So because of that ionic bond, there is electrostatic attractions between the metal and ligand. So these electrostatic attractions are maybe ion-ion interactions or ion dipole interactions. So ion-ion interactions. So ion-ion interactions when both the metal and ligands are ions. Metal is always positive charge and ligand is if ligand is negative charge, then there is a ion-ion interactions, right? The second, the ion dipole interactions. The metal is charged, if metal having positive charge, and ligand is neutral. In that case, the interaction between these two, metal and ligand, is ion dipole interactions, right? So that is third postulate. So what is the fourth postulate? So this theory mainly concentrated on metal d orbitals. How many d orbitals? So you are having 5 d orbitals: dxy, dyz, dzx, dx square y square, and dz square. So 5 d orbitals. So now ligands approaching with their electron density, there is a electron repulsion. Metal having the electrons in the metal d orbitals, here having electrons, and ligands approaching electrons with their electron density approaching this metal atom, donating electrons to this into the vacant orbitals of this metal atom, right? So and then there is the electron repulsion. Because of that electron repulsions, the energy of 5 d orbitals rises somewhat. That means, so before approaching ligands, before donating electrons of ligand, before donating lone pair of electrons with ligand, the metal d orbitals are all all 5 d orbitals are same energy. Okay, all 5 d orbitals have same energy. Next, under the influence of ligand, the metal d orbitals will split. So next postulate, what is the fifth postulate? Under the influence of ligands. Okay, under the influence of ligands, if ligands are approaching with their electron density along the axis or in between the axis, if they are donating electrons along the axis, in that case Eg are having higher energy, because what are the Eg orbitals? Dx square y square and dz square. Both are loops are along the axis, dx square y square and dz square. Both the orbitals electron density along the axis. Now, right? So ligands electron density along the axis. Now there is a more electron repulsion between the Eg orbitals and ligand orbitals. In that case, more repulsions, more energy. So Eg orbitals are higher energy, T2G orbitals are lower energy. In case ligands are donating electron density in between the axis, in that case T2G orbitals experience more repulsion, more energy, and ligand orbitals and EG orbitals having lower energy. Okay, so in that way, that means under the influence of ligands, the metal d orbitals split into two sets. That splitting is called Kirsta field splitting, and the difference is called, which is indicated by delta. So that difference is called Kirsta field stabilization energy, CFSE. Kirsta field stabilization energy, CFSE, which is indicated by delta. Right. So that is postulate number 5. So postulate sixth postulate was, sixth assumption was, what is sixth assumption? So magnetic property. So magnetic property which is depends upon the extent of this d orbital splitting. If the d orbital splitting is increases, the electrons, when pairing the electrons, when filling the electrons instead of going to the higher energy, because of this gap is more, so because of this more energy gap, instead of electrons going into the higher energy, the electrons are paired up in the lower energy. So pairing of electrons increases. That means unpaired electrons decreases. Because of pairing, the unpaired electrons decreases, hence magnetic character decreases. Understood? If magnetic property depends upon the extent of metal d orbitals. If metal extent of splitting increases, the lesser number of unpaired of electrons, hence less will be your magnetic character, right? And the last point is color. Color of transition metal complex can be explained by the electron transitions between these various d orbitals. So T2, when giving white light to this complex, this light can absorb by this electron and exert into the higher energy, again which comes back into the lower energy by emitting some wavelength radiations. That wavelength radiation corresponds to specific color. So that color is shown by this complex. Okay, right? So in that way, the color of complex compounds can be explained based on electron transition between the ligands.